close your eyes, right now. Do not open them for 10 seconds. Feel what happens. The world does not vanish. It shifts. The sounds in the room get louder. Your breathing becomes audible. Something in the back of your skull loosens, as if a muscle you did not know was clenched has quietly let go. That loosening is not a feeling. It is an electrical event. The moment your eyelids come down, the back of your brain begins producing a rhythmic pulse of activity that was suppressed every second your eyes were open. And what that pulse does inside your skull over the next 60 seconds is more elaborate, more precisely coordinated, and more consequential for your health than almost anything a physician could prescribe for the same duration. Here is what is actually happening inside you. Your brain weighs about 1.4 kilograms, 2% of your body mass, yet it consumes 20% of every calorie you eat. That is roughly 0.3 kilowatt hours per day, more than 100 times the daily energy draw of your smartphone. And within that already ravenous organ, one system devours more resources than any other: vision. The visual system is one of the most energy-intensive networks in the entire brain. The retina alone consumes more oxygen per gram of tissue than the brain itself. Margaret Wong Riley at the Medical College of Wisconsin has spent decades mapping energy metabolism across the visual pathway, tracing cytochrome C oxidase activity from the retinal photoreceptors through the lateral geniculate nucleus to the primary visual cortex. She has documented that area V1, the sheet of neural tissue at the very back of your skull where raw visual signals first arrive in the cortex, maintains some of the highest metabolic rates of any cortical region. Within V1, the layer that receives input from the thalamus, layer 4, burns more energy than any other layer. The magnocellular pathway, which processes motion, burns more than the parvocellular pathway, which processes fine detail and color. The brain does not distribute its visual resources evenly. It pours fuel into the channels most critical for survival, tracking movement above all. Peter Lenny, a vision scientist formerly at New York University, estimated that visual processing accounts for roughly 44% of the brain's total energy consumption. 44%. Nearly half of all the glucose your brain burns goes toward constructing the three-dimensional moving color world you see when your eyes are open. Now consider what happens when you take that system offline. When you close your eyes, glucose consumption in the visual cortex drops. Not by a trivial amount. Opening your eyes onto a complex dynamic visual scene can increase energy use in that cortex by up to 50% compared to the eyes closed state. The visual system does not shut down when the eyelids close. The neurons are still there, still firing at baseline rates, still maintaining their membrane potentials. But the massive computational load, parsing edges, tracking motion, constructing depth, identifying faces, updating object representations, feeding that torrent of data forward into attentional and decision-making networks, is suddenly reduced. And the brain, which operates on a fixed energy budget that does not increase with demand, reallocates. Nili Lavi and colleagues at University College London demonstrated this reallocation directly. Using broadband near-infrared spectroscopy to measure cellular metabolism in the visual cortex, they showed that when one region of the visual system increases its energy use, other regions decrease theirs in a precisely synchronized push-pull pattern. The brain trades energy between attended and unattended processing like a fixed-sum budget. When you close your eyes, the entire attended visual budget becomes available for reallocation to other systems. Where does it go? Think about what your brain was doing before you closed your eyes. Every second that your eyes were open, roughly 126 million photoreceptors in each retina were converting electromagnetic radiation into electrochemical signals. Those signals traveled through 1.2 million retinal ganglion cell axons, bundled together as the optic nerve, to the lateral geniculate nucleus of the thalamus, and from there fanned out into the primary visual cortex, where billions of synaptic events per second constructed the stable, seamless, three-dimensional world you call seeing. The computational load of this process is staggering. Edge detection. motion tracking across the full visual field, binocular disparity calculations for depth perception, object recognition requiring comparison against a lifetime of stored visual templates, face identification, a task so computationally specialized that the brain devotes an entire subregion of the fusiform gyrus to it, color constancy corrections, compensating for changes in ambient light so that a red apple looks red in fluorescent light and in sunlight. All of that stops when the eyelids come down, not the hardware, the workload. And because the brain operates on a fixed energy budget that cannot simply generate more glucose on demand, the resources that were powering that computational torrent become available for reallocation. It goes inward. The first thing that happens when you close your eyes is one of the oldest observations in all of neuroscience, and for nearly a century it was misunderstood. In 1929, a German psychiatrist named Hans Berger was recording electrical signals from the surface of the human scalp for the first time. He had been working on this project in near secrecy for 5 years at the University of Jena, using a double-coil galvanometer more sensitive than anything his predecessors had access to. What he saw was a rhythmic oscillation of roughly 10 cycles per second, rolling in smooth waves across the back of the head. He named it the alpha wave. The critical detail was this. The alpha wave appeared most strongly when his subjects lay still with their eyes closed. The instant they opened their eyes, the wave collapsed. Berger called this phenomenon alpha blocking. The prominent British neurophysiologist Lord Edgar Adrian replicated Berger's observations and confirmed them, establishing electroencephalography as a legitimate window into the living human brain. When the eyelids came down, the alpha rhythm returned. When they opened, it vanished. For decades, neuroscientists assumed this was simply the brain idling, the visual cortex with nothing to do, defaulting to a slow hum the way a car engine settles to a low idle when you take your foot off the accelerator. That interpretation is wrong. Alpha waves are not the sound of a brain doing nothing. They are the sound of a brain actively suppressing its own visual machinery. During periods of increased alpha band synchronization, neural spiking rates in the cortex are measurably reduced. Single-cell recordings have confirmed that when alpha power rises, individual neurons in the visual cortex fire less frequently. The alpha rhythm is not passivity. It is inhibition. Targeted, rhythmic, precisely timed inhibition of the visual cortex, generated by networks of GABAergic interneurons, the same class of inhibitory cells that regulate excitability throughout the entire brain. The frequency is specific, 8 to 13 hertz, with a peak near 10 cycles per second. The amplitude is measurable, 20 to 60 microvolts, waxing and waning in spindles that last 1 to 2 seconds each. And the topography is consistent across virtually every human brain ever tested. Strongest over the parieto-occipital region, right where your hand would rest if you cupped the back of your skull. When you close your eyes, this rhythm surges. Within seconds, alpha power across the occipital cortex increases substantially. Robert Barry and colleagues at the University of Wollongong measured electroencephalographic activity from 28 participants during both eyes closed and eyes open resting conditions and confirmed reductions in mean absolute power across delta, theta, alpha, and beta bands from eyes closed to eyes open, with alpha showing the most widespread and dramatic shift. Skin conductance levels, a marker of sympathetic arousal, increased significantly when the eyes opened and correlated negatively with alpha levels during the eyes closed state. The higher the alpha power, the lower the physiological arousal. The brain is not resting. It is actively gating the visual system, throttling down the most energy-expensive sensory channel it operates, and freeing resources for processes that can only run efficiently when the fire hose of visual data stops flowing. Ole Jensen and Ali Mazaheri at the Donders Institute for Brain, Cognition and Behavior in Nijmegen proposed a framework they called gating by inhibition. Their argument, published in 2010, is that alpha oscillations are not a passive marker of idleness, but an active mechanism for routing information through the brain. When the brain needs to suppress processing in one region to prioritize another, it does so by increasing alpha power in the region to be silenced. The alpha rhythm is a gate. When it rises, the gate closes. Information from that region is blocked from reaching downstream processors. This means that when you close your eyes and alpha power surges across the visual cortex, the brain is not merely reducing noise. It is performing an act of neural triage. It is reallocating bandwidth. The visual gate closes, and the gates to internal processing, memory, self-reflection, autonomic regulation, open wider. The elegance of this system is that it requires no conscious decision. The physical act of lowering the eyelids triggers the thalamic shift that triggers the alpha surge that triggers the gating. Your conscious mind does not choose to suppress the visual cortex. The architecture does it automatically. And while the back of the brain quiets down, something very different is waking up deeper inside. In 2001, Marcus Rachel at Washington University in St. Louis published a paper that redefined how we understand the resting brain. He and his team had been studying brain activity using positron emission tomography and functional magnetic resonance imaging, and they kept finding the same anomaly. When research participants were asked to stop performing tasks, to simply lie still with their eyes closed, a specific set of brain regions reliably increased in activity, not decreased, increased. The regions formed a network. The medial prefrontal cortex, tucked behind the center of your forehead. The posterior cingulate cortex, buried deep along the midline at the back of the brain. The inferior parietal lobules, sitting laterally above the ears. And critical portions of the medial temporal lobe, including the hippocampus. The seahorse-shaped structure curled inside each temporal lobe that is most essential to the formation and retrieval of memory. Rachel called this the default mode network. The name was controversial because it implied the brain has a default state, a mode it returns to when not occupied with the outside world. The implication was profound. The most natural state of the human brain is not paying attention to the external environment. It is turned inward, self-referencing, time-traveling, simulating. And closing your eyes is one of the most reliable ways to activate it. Victor Costumero and colleagues at the University of Lisbon used functional magnetic resonance imaging on two independent groups, 105 eyes-closed participants and 63 eyes-open participants, and found that when the eyes are closed, the primary visual cortex couples positively with the default mode network and the sensorimotor network. When the eyes are open, V1 couples instead with the salience network, the system responsible for detecting threats and novelty in the environment. They replicated these findings using an independent open-source dataset, strengthening confidence in the result. Closing the eyes does not merely reduce visual input. It restructures the functional architecture of the brain. The entire organ shifts from an externally oriented threat monitoring configuration to an internally oriented self-referential configuration. The default mode network handles some of the most distinctly human operations the brain performs. Autobiographical memory retrieval, planning and imagining future scenarios, theory of mind, the capacity to model what another person is thinking or feeling, moral reasoning, creative ideation, the kind of loose associative thinking that produces insight and novel solutions. And perhaps most consequentially for the 60 seconds you spend with your eyes closed, the default mode network coordinates with the hippocampus to consolidate recently acquired memories into long-term storage. This is where it becomes practical. Michaela Dewar, a psychologist at Heriot-Watt University in Edinburgh, published a series of studies between 2007 and 2014 demonstrating that a brief period of quiet, eyes-closed, wakeful rest after learning significantly improves memory retention. In one study, participants who rested with their eyes closed for just 10 minutes after hearing a short story recalled substantially more of it when tested 7 days later than participants who spent those same 10 minutes engaged in a simple cognitive task. The effect was not subtle. It persisted over a full week. The mechanism appears to be neural replay. Lauren Frank and colleagues at the University of California, San Francisco demonstrated that during quiet waking rest, Hippocampal neurons fire in compressed sequences that recapitulate recent experiences. The same patterns of activity that occurred during learning replay themselves at accelerated speed during stillness. These replay events occur during sharp-wave ripples, brief bursts of synchronized activity in the hippocampus that last only 50 to 100 milliseconds each. They are the brain's way of rehearsing what it just learned without requiring you to consciously rehearse anything at all. Sharp-wave ripples happen during sleep. That has been known for decades. What is newer and more striking is that they happen with equivalent frequency during awake rest. Matthias Carr, Shantanu Jahav, and Lauren Frank published in Nature Neuroscience in 2011 that hippocampal replay during waking rest may serve as a physiological substrate for both consolidation and retrieval of memory. The hippocampus during those quiet moments is running its own internal rehearsal loop, strengthening the synaptic connections that will allow a memory to survive from short-term hippocampal storage into the more durable architecture of the neocortex. A separate study by Walmsley and Humiston demonstrated that even motor skill memory benefits from eyes-closed rest. Participants trained on a finger-tapping sequence and then either rested quietly with their eyes closed or performed an unrelated task for 15 minutes. The resting group showed significant performance improvements on the sequence when retested, mirroring effects previously attributed only to sleep. The brain consolidates motor skills and verbal memories using the same offline replay machinery, and it does not need full sleep to access it. It needs stillness. A 2025 meta-analysis by Wang and colleagues, compiling 37 studies with 82 independent comparisons, confirmed a significant effect of wakeful rest on memory consolidation. The overall effect size was moderate, Hedges's G of 0.448, and the benefit persisted for at least 7 days. Older adults showed even larger benefits than younger adults, which is precisely the demographic most likely to feel that their memory is failing them. The irony is pointed. The population that worries most about cognitive decline may benefit most from the intervention that looks the most like doing nothing. The brain needs its eyes closed, not to stop working, but to finish work it started while they were open. And while the hippocampus is replaying your memories, while the default mode network is running its internal simulations, the alpha wave surge in the occipital cortex is doing something else entirely to the rest of your body. The rhythmic inhibition produced by alpha oscillations is generated by GABAergic interneurons in the cortex and modulated by thalamocortical circuits. GABA, gamma-aminobutyric acid, is the chief inhibitory neurotransmitter of the mammalian central nervous system. When GABA binds to its receptor, a protein complex called the GABA-A receptor, it opens a chloride ion channel. Chloride ions flow into the cell. The interior of the neuron becomes more negative. This hyperpolarizes the cell. A hyperpolarized neuron is harder to excite, harder to fire. The cell becomes quiet. Multiply this across millions of neurons in the occipital cortex, synchronized at 10 cycles per second, and you get the alpha rhythm. A coordinated wave of inhibition sweeping through the visual system like a tide retreating from the shore. But GABA does not stay local. The thalamus, a walnut-shaped relay station sitting at the center of the brain, generates its own rhythmic bursts of activity in the alpha frequency range and broadcasts them to the cortex. Matti Lörinx and colleagues, publishing in the journal Neuron, demonstrated that phasic inhibition during the alpha rhythm frames the timing of thalamic relay mode firing. The thalamus itself is modulating how information flows through the brain on a cycle-by-cycle basis, using the alpha oscillation as a temporal framework. When your eyes close and alpha power rises, this thalamocortical inhibitory loop strengthens. The consequence extends far beyond the visual system. The thalamus connects to virtually every region of the cortex. A shift in thalamic rhythmicity alters the operating state of the entire brain. It is not a local event. It is a global reconfiguration, initiated by the simplest possible physical action, the lowering of 2 eyelids. And because the brain does not exist in isolation from the body, this reconfiguration cascades downward through the autonomic nervous system. Your eyes are not simply cameras. They are physically wired into the autonomic nervous system through cranial nerve 3, the oculomotor nerve, which carries parasympathetic fibers originating in the Edinger-Westphal nucleus of the brainstem. When your eyes are open, the ciliary muscle in each eye is under continuous parasympathetic control, actively adjusting focus for near and far vision. The pupil dilator and constrictor muscles are under constant sympathetic and parasympathetic modulation, balancing the amount of light reaching the retina. The 6 extraocular muscles are firing and adjusting dozens of times per second during saccades and microsaccades. Tiny eye movements you are not even aware of making, each one requiring motor commands from brainstem nuclei. When you close your eyes, all of this stops. The ciliary muscle relaxes. The pupil constrictor releases. The constant barrage of oculomotor commands from the brainstem ceases. And because the brainstem nuclei controlling the eyes sit in close anatomical proximity to the nuclei controlling the vagus nerve, the parasympathetic shift initiated by eye closure radiates downward through the 10th cranial nerve to the heart, the lungs, and the visceral organs. The vagus nerve is the longest cranial nerve in the body. It carries 75% of all parasympathetic fibers. When vagal tone increases, heart rate decreases, heart rate variability increases, respiratory rate slows, and the balance of the autonomic nervous system shifts from sympathetic dominance toward parasympathetic recovery. This shift does not require minutes of meditation. It does not require a breathing technique. The anatomical wiring between the oculomotor system and the vagal system means that the simple act of closing the eyes and releasing the visual motor apparatus begins the parasympathetic cascade within seconds. Narrow, focused vision activates the sympathetic branch. Your visual field constricts when you are stressed, afraid, or concentrating intensely on a threat. This is not metaphorical. It is the literal activation of sympathetically driven pupil dilation and the narrowing of attentional scope to foveal processing. Softened or absent visual focus activates the parasympathetic branch. The pupils constrict. The extraocular muscles release. The brainstem shifts state. Closing the eyes is the most complete form of visual disengagement available to a conscious human being. The downstream physiological effects are measurable. Heart rate variability, the variation in time between consecutive heartbeats, is one of the most widely used markers of parasympathetic tone in clinical research. Higher heart rate variability indicates greater vagal influence on the sinoatrial node and correlates with better cardiovascular health, lower inflammation, and improved emotional regulation. Low heart rate variability is associated with anxiety disorders, depression, post-traumatic stress, and increased risk of cardiovascular mortality. Reduced heart rate variability is also one of the defining features of the chronic stress state. The sympathetic branch dominates. The parasympathetic branch is suppressed. The heart beats with metronomic regularity because the vagal brake is not being applied. The organ that should be responsive and variable becomes rigid and locked. When you close your eyes, even briefly, the brainstem receives a signal that the visual motor system no longer requires its full vigilance. The tonic sympathetic activation that accompanies open-eyed alertness begins to recede. Vagal outflow to the sinoatrial node increases. Heart rate drops by a few beats per minute. The intervals between heartbeats become more variable. The system loosens. This is not relaxation in the colloquial sense. It is a measurable shift in the ratio of sympathetic to parasympathetic autonomic activation, initiated not by willful relaxation, but by the physical cessation of visual motor processing. The anatomy does it for you. 60 seconds. That is how long you have been sitting with your eyes closed in this thought experiment. In those 60 seconds, the back of your brain suppressed its most expensive system through a coordinated GABAergic inhibitory wave pulsing at 10 hertz. The freed metabolic resources shifted to internal networks. The hippocampus began replaying recent experience at compressed timescales, running rehearsal loops through sharp wave ripples lasting 50 to 100 milliseconds each. The default mode network activated, connecting self-referential processing centers across the medial prefrontal cortex, the posterior cingulate, and the temporal lobes. The thalamocortical loop shifted state, altering the rhythmic framework through which information flows across the entire cortex. And the autonomic nervous system tilted toward parasympathetic recovery, lowering heart rate and increasing heart rate variability through vagal pathways physically connected to the muscles of your eyes. Not one of these processes required you to think. Not one required effort, technique, or training. They are hardwired. They happen the instant the eyelids descend. Now, how strong is the evidence for each of these mechanisms? The alpha wave response to eye closure is one of the most replicated findings in all of neuroscience. It has been documented continuously since 1929, confirmed with modern high-density electroencephalography in hundreds of studies across populations spanning infants to the elderly. This is as solid as anything in human neurophysiology. The coupling of V1 with the default mode network during eye closure has been demonstrated by Costumero and colleagues in 2 independent datasets using functional magnetic resonance imaging. The replication using an open-source shared dataset strengthens the finding considerably. This is strong evidence, though the precise functional significance of the coupling, what the default mode network is doing differently when it receives this new input from V1, remains under active investigation. The memory consolidation benefit of wakeful rest is supported by a 2025 meta-analysis showing a moderate and significant effect size across 37 studies. The effect appears most robust for declarative memory tested by recall rather than recognition, and most pronounced in older adults. However, the literature is not without null results. Some individual studies have failed to detect a benefit, and there is meaningful variability in effect sizes across studies. The hippocampal replay mechanism during waking rest has been directly observed in rodents at the single neuron level. In humans, indirect evidence from functional imaging supports the same mechanism, but direct single neuron recordings during awake rest in humans remain limited. This is strong but partially indirect evidence. The autonomic shift following eye closure is physiologically consistent and supported by the known anatomy of cranial nerve pathways. It has not been isolated and measured with the same precision as the alpha wave response. I would call it mechanistically sound, well grounded in neuroanatomy, but awaiting dedicated experimental confirmation in controlled studies that specifically isolate eye closure from other relaxation behaviors. The anatomy says it should work this way. The clinical observations are consistent. The definitive experiment has not yet been published. I am not overselling. I am telling you exactly what each piece has behind it. There is a class of drugs prescribed to approximately 30 million people in the United States alone. Benzodiazepines, diazepam, lorazepam, alprazolam, brand names you have almost certainly heard. They are prescribed for anxiety, insomnia, muscle tension, and seizure prevention. The global market generates billions of dollars annually. Here is how they work at the molecular level. Benzodiazepines bind to a specific allosteric site on the GABA-A receptor, the same receptor system whose inhibitory activity generates the alpha rhythm in your visual cortex. They are positive allosteric modulators. That means they do not activate the receptor directly. They change its three-dimensional shape so that when GABA arrives at the binding site, the chloride channel opens more frequently. More chloride flows in. The neuron hyperpolarizes more deeply. Neural excitability across the brain decreases. The patient feels calm. The anxiety recedes. The muscles loosen. Sleep becomes possible. The molecular cascade is the same cascade. GABA binds to the GABA-A receptor. Chloride ions enter the cell. The neuron hyperpolarizes. Firing rates decrease. Cortical excitability drops. Sympathetic tone eases. The downstream effects: reduced neural excitability, lowered sympathetic arousal, decreased subjective anxiety, muscle relaxation, are the pharmacological cousins of the neurological events that begin the instant you close your eyes and the alpha rhythm surges. The differences are important, and they are real. A benzodiazepine acts globally, binding to GABA receptors throughout the entire brain, not selectively in the visual cortex. The magnitude of inhibition produced by a clinical dose of diazepam vastly exceeds the natural alpha-mediated inhibition of eye closure. Benzodiazepines carry risks of tolerance, physical dependence, withdrawal syndromes, cognitive impairment, increased fall risk in the elderly, and in combination with opioids or alcohol, fatal respiratory depression. They alter the GABA system so profoundly that after chronic use, the brain's own inhibitory machinery downregulates, producing the very anxiety the drug was prescribed to treat. The alpha wave does none of these things. But the pathway is the same. The neurotransmitter is the same. The ion channel is the same. The direction of effect, inhibition of neural excitability through enhancement of GABAergic signaling, is the same. One costs nothing, requires no prescription, produces no side effects, has no withdrawal syndrome, and has been available to every human being with functioning eyelids since the evolution of the cerebral cortex. The other generated billions in global pharmaceutical revenue last year. I am not telling you to stop taking medication your doctor prescribed. If a benzodiazepine was prescribed, it was prescribed for a reason, and the dose is calibrated to a severity of symptoms that 60 seconds of eye closure cannot match. A panic attack cannot be stopped by closing your eyes. A seizure disorder cannot be managed by alpha waves alone. The pharmaceutical version exists because some people need more inhibition than the body can produce on its own. But the pathway is not foreign. Your brain already speaks this molecular language. It has been speaking it every time your eyelids close since the first day of your life. The drug is amplifying a conversation your neurons already know how to have. There is a person listening to this right now, 67 years old, maybe 72, retired or approaching it, sleeps poorly and has for years, has been told by a doctor, perhaps more than one doctor, to practice relaxation techniques, has tried meditation and found it frustrating because the mind will not stop wandering, has been prescribed something for sleep or anxiety, a small white pill, and does not love the way it makes them feel in the morning, foggy, thick, as if the night's rest came at a cost, knows in some inarticulate way that the answer should be simpler than all of this, that the body should already have the tools. It does. Your grandmother knew. When you were a child and you came inside crying, overwrought, buzzing with some catastrophe that felt enormous at age 6, she did not hand you a prescription. She did not teach you diaphragmatic breathing. She did not guide you through a body scan meditation. She said the same thing grandmothers have been saying for centuries, in every language, on every continent. Close your eyes and count to 10. The count is a distractor. It occupies the dorsolateral prefrontal cortex, preventing ruminative loops from taking hold. It gives the mind a simple task so that it does not spin into recursive worry. But the real work, the physiological intervention, is done by the first 3 words. Close your eyes. The alpha rhythm surges. 10 hertz. The visual cortex quiets. 44% of the brain's energy budget begins to redistribute. The hippocampus starts its compressed replay, 50 millisecond sharp wave ripples rehearsing whatever was learned that day. The default mode network comes online, linking the medial prefrontal cortex to the posterior cingulate to the temporal lobes. The thalamus shifts state, altering the rhythmic framework of cortical communication. The oculomotor apparatus relaxes. The brainstem shifts. The vagus nerve carries the parasympathetic signal downward. Heart rate drops. Heart rate variability rises. Breathing slows. The autonomic nervous system tilts toward recovery. All of it, in 60 seconds, without instruction, without equipment, without cost, without risk. Your grandmother did not know the word GABA. She did not know what an alpha oscillation was. She had never heard of the default mode network. She did not know that the Edinger-Westphal nucleus sits adjacent to the dorsal motor nucleus of the vagus. She did not know that sharp wave ripples in the hippocampus replay compress sequences of recently encoded experience during wakeful rest. But she knew what worked. She knew it because 1,000 generations of grandmothers before her knew it. The instruction was not superstition. It was not folk placebo. It was a precisely correct physiological intervention delivered in 6 words by a woman who could not have named a single structure in the brain. And now you know why it works. The next time you are overwhelmed, overstimulated, unable to sleep, unable to think clearly, unable to remember what you just read, do the simplest thing available to you. Do not reach for a device. Do not reach for a bottle. Do not try to meditate. Do not try to breathe in any particular pattern. Do not do anything at all. Close your eyes. Count to 60. The brain will handle the rest.